the area of topological quantum computation. So we want to sort of leverage topological order and its nice properties as a phase of matter for the purposes of storing and manipulating quantum information. And so the sort of simplest and most well-known example of such a topological quantum code is the surface and toric code, which I'm sure people are familiar with. But just to sort of compare, here we have abelian anyons, and the sort of memory properties of the toric code come from the non-trivial anionic statistics of the quasi-particles in the toric code. In particular, we have these abelian braiding statistics, where when we bring two anyons around each other, they can pick up some complex phase. But in order to do computation and not just information storage, we can't just work with these phases. We need to generalize to some more complicated form of braiding statistics, and this is where non-abelian excitations come in. So we sort of generalize to anyons which have some internal Hilbert space, which I indicate by this index, additional index. And when I braid them, this is equivalent to doing some unitary transformation on this internal Hilbert space. And this unitary and sort of classifying which types of unitaries we can get through different topological orders forms the backbone of how we envision doing computation with these non-abelian topological codes. So to give, again, just a brief introduction so everyone's on the same page of the particular types of non-abelian models I'll be considering today. I'll be considering quantum double models, which are sort of generalizations of the toric code to some other finite group. And in particular, if we have some finite group which is non-abelian, then the anyons, which are the elementary excitations of the quantum double Hamiltonian, will be non-abelian in general. So I sort of care about using these non-abelian anyons for building some quantum gates. And the motivation for thinking about this type of computation now, I would say, is that these non-abelian phases and non-abelian excitations are more and more accessible experimentally. Just to name a few, to flash a few papers that have come out within the past 2 years on sort of experimental realizations of either non-abelian topological order or non-abelian excitations defects embedded inside an abelian topological order, including work done by people here at Cornell. And of course, as I mentioned, such phases and excitations can be used for quantum computation and sort of most importantly for theoretically fault-tolerant quantum computation. And so if we want to actually do such computation, that will entail having to have some level of fine control over these non-abelian excitations. And the content of this talk is really both trying to come up with practical ways that we can sort of control these non-abelian excitations in near-term devices, and also gain some deeper conceptual insight into the structure of the circuits that you need to create and move these non-abelian anyons. So so the overall goal is said to better understand how to control these non-abelian anyons, specifically in quantum double models, but with a view towards practical implementations of quantum computation on near-term devices. So first, how do we create non-abelian excitations, and how is it different than their abelian counterparts? So abelian anyons, we create them. They're created at the ends of string operators, which in the case of the toric code are just tensor products of on-site operators, but in general, there'll be some finite depth circuit. But non-abelian anyons, they instead have to be created by some generalized object known as a ribbon operator, which will generically, if I'm trying to do it unitarily, will be linear depth in the length of the ribbon. And intuitively, I can understand this restriction from the existence of this internal Hilbert space, from the fact that I can store information inside of a non-abelian anion. I shouldn't be able to sort of move it around my system arbitrarily fast, just from sort of causality reasons. And to give you some notion of what this ribbon operator actually looks like in practice, Kitaev, in his original paper, introducing the quantum double models, also writes down these ribbon operators to create anions, and they look sort of something like this, where the operation that you have to do farther and farther along the ribbon depends on all of the steps previous, and so you can see how this quickly might get very unwieldy to work with. So yeah, just to give you a sense of sort of the state of the literature and how this work will fit in. So yeah, as I said, in 2005, Kitaev introduces these ribbon operators, which create non-abelian excitations inside quantum double models. But he actually has this quote in this paper where he says, "I do not know how to deduce an expression for such operators. I will just give an answer and show you why it's correct." So sort of demonstrating that although we know that these are the right operators, we don't necessarily have a good conceptual understanding of why they look the way that they do. And then a few years later, there's this paper by Bauman and Martin Delgado where they give sort of an exhaustive mathematical exploration of these ribbon operator properties. But again, sort of maybe a physical intuition is lacking. And then in 2019, Bo and Shi proved this unitary bound on the depth of non-abelian ribbon circuits. And then more recently, Sergei Bravi and collaborators wrote down, sort of showed that if we are allowing for measurements and feedback, we can make certain types of non-abelian ribbons efficient. And they were doing this sort of using some clever circuit optimization and gate teleportation tricks. And sort of what I'm going to advocate for in our work is that we are sort of providing both practical feasibility and conceptual clarity. So practical feasibility, we'd want sort of maybe few body gates and efficient circuits where it's possible, which is ideal for near-term noisy devices with limited coherence time. And such sort of practical-minded ribbon operator implementations have been shared in the literature before, including this work I just talked about by Sergei Bravi. But I think a space that our paper can slot into is sort of introducing maybe a conceptual framework for understanding how the structure of these non-abelian ribbons comes about, which is what I will talk about now. So the main idea, I guess, to give you an overview before I dive into it, the main construction is sort of this four-step process. So first, we start with some topological order that we care about. Maybe it's non-abelian intrinsically, or maybe it's abelian, but it has some interesting non-abelian symmetry defects. And then the key idea is that we're going to leverage some duality mapping to go in some small region of our topological order to a simpler dual theory. And I'll explain what I mean by simpler. And then, leveraging our knowledge of this maybe simpler structure of this dual theory, we can create some precursor excitation and apply some finite depth circuit in this simpler theory. And then we sort of rezip our topological order back up, and we're left with the desired anion or defect. So this is the framework that we're going to build around. So specifically, the duality that I'm going to be discussing today is the Kramers-Vonnier duality. And by the simpler property that I mean is that this Kramers-Vonnier duality is mapping us between a topological order with long-range entanglement back to a trivial paramagnetic phase that has some global symmetry. And so this Kramers-Vonnier duality is allowing me to map between my more complicated topological order and some simpler paramagnet, which sort of I can understand the excitations of better. So again, just to have everyone on the same page, how does this Kramers-Vonnier duality work for the simplest example, which is Z2 paramagnet to the Z2 toric code? So the transformation rules for my operators under Kramers-Vonnier duality are as follows. An X operator on a vertex gets mapped to the vertex term of the toric code, and a pair of Z operators on the paramagnet side gets mapped into a single Z on an edge, which, so I get my toric code vertex stabilizer for free automatically. And I then get the plaquette term from the redundancy that was originally on the paramagnetic side, where a product of my pair of Z's around a plaquette is the identity. So I get that the product of Z's around the edges of a plaquette become identity on the toric code side. So yeah, so this duality is, it's a conceptual one, but it's also a physical operation that I can do to my system. I can think of it as some quantum circuit that I can apply, and this is going to be important for actually implementing this unzipping procedure that I talked about. And I can realize this in several ways. I could do it in linear depth, extensive depth, via some unitary circuit. Or I could do it for certain types of symmetries. I can do it with an adaptive circuit in finite depth. But the key idea is that I'm not only thinking of this duality as sort of a theoretical tool, but also as a actual operation that I can do on my quantum computer to my physical qubits. And so to give, again, a toy example of how this Kramers-Vonnier duality helps us understand the structure of excitations on the toric code on the topological order side, we can again go back to the Z2 case and compare sort of excitations and operators on one side of the mapping versus the other. So for instance, we have a pair of E anions in the toric code. We create that at the ends of a string operator of Z's. And if I push my string of Z's backwards through the Kramers-Vonnier map, I'm just left with two charge operators at the ends of my string, which is just a charge pair on top of my paramagnet ground state. So I have this mapping between charges on top of the paramagnet and sort of charged anions in my topological order. I also have some correspondence between closed loops of M anions and truncated symmetry operations on my paramagnet. So if I have a closed M string, I push it back through the Kramers-Vonnier map, I get sort of the bulk symmetry membrane that would fill in that M anion loop. So this is the sort of basic idea, which we can generalize to more complicated non-abelian topological orders, but the conceptual idea is the same. So to give a non-abelian example, we can consider the Z3 qubit toric code, which is itself non-abelian, but it is itself abelian, but I'm going to make it non-abelian in a second. So we start with the Z3 toric code, which I just now define with clock and shift Paulis instead of Z2 Paulis. But the structure of the Hamiltonian looks basically the same. I have a vertex and plaquette terms. Now, however, I have two kinds of M and E anyons, which are related by this charge conjugation symmetry, which takes X to X dagger and Z to Z dagger. And at the level of the anion theory, it just interchanges the two kinds of anions. And I can obtain a non-abelian theory from the Z3 toric code by gauging this charge conjugation symmetry. And I actually get the so-called S3 topological order from this. Intuitively, I can see why I will get something non-abelian, because I said that this charge conjugation symmetry is sort of interchanging E and E squared. And so when I promote the charge conjugation symmetry to a gauge symmetry, it sort of packages the E and E squared anyons together into one anion. And sort of one dimension 2 anion, where the E and the E squared are now internal states of one non-abelian anion rather than distinct anions of their own. And the same thing happens to the M and the M squared anion. So we can sort of use the fact that we have this duality between the Z3 toric code and the S3 non-abelian topological order to write down ribbon operators for these non-abelian S3 anyons. And the idea is just to sort of undo the gauging procedure in a small region, go back to the Z3 toric code where these anyons are abelian, move them in finite depth, create them with their string operators, and then sort of re-gauge the symmetry to return to S3. To give another example, S3 has, or Z3, if I'm just considering Z3, it already has some non-abelian excitation in it without needing to go to S3, which is a symmetry defect rather than a deconfined anion. So the charge conjugation symmetry, I can introduce a symmetry defect line just by applying charge conjugation in a finite region. And how this will impact my anions is that if I create an E and an E squared pair, if I bring the E squared across this dotted line into the region where I applied charge conjugation, it will get turned into an E anion. But if I bring it back out again, it will turn back into an E squared. And so overall, I haven't really done anything non-trivial here because if I want to create a closed loop of these anion, this E anion pair, if I want to bring them back together, any closed loop will intersect my defect line in an even number of times. So the anion pair will always fuse back to the vacuum. I've just sort of done maybe a basis change in this dotted region. But I can envision doing something more non-trivial where I have an open defect line. And now when I bring my E anion through, it crosses once, but it might cross only once if it braids non-trivially with the end of the line. And now I have a single E anion, but this sort of seemingly violates sort of charge constraints on my system. I can't have a single anion, but the way to get around this is that this defect must absorb the extra abelian anion that I'm missing. And so it itself has to be non-abelian with some internal Hilbert space to account for the fact that it can sort of absorb an abelian anion. And so you can ask the question, well, how would we actually create such a defect pair if I had like a prepared Z3 toric code? Creating the closed defect line is straightforward. I just apply my single site charge conjugation operator in some finite region. But creating the open line is less clear. So we're going to, again, leverage Kramers-Vonnier duality. So we note that the Z3 paramagnet and the Z3 and the Z3 toric code share the charge conjugation symmetry, and that if I push the charge conjugation symmetry through the Kramers-Vonnier map, it sort of remains the same. It just acts on different degrees of freedom. And a nice thing is that this charge conjugation symmetry acts trivially on the paramagnet. And so if I now want to ask, well, I know that the full bulk symmetry transforms trivially under this Kramers-Vonnier map, but how does a single site of charge conjugation transform? Well, I can use the transformation rules, which I've listed at the top here for the Z3 Kramers-Vonnier map. And I can just express the charge conjugation operator as a sum over products of clock and shift operators, Pauli Z3X and Z's, and which leads me to some expressions for pushing a single site charge conjugation operator through from either the topological toric code side or the paramagnet side through the Kramers-Vonnier map. And due to the fact that the Kramers-Vonnier map I can see from the transformation rules that a single X on the paramagnet side maps to something local on the toric code side versus a single Z on the toric code side maps to something local on the paramagnet side. I can only achieve a local expression for this single site charge conjugation operator if I don't fully push it through the Kramers-Vonnier map. So I'm left with action that is on both sides, on the pre-gauged and on the topologically ordered degrees of freedom. And this is why I was emphasizing the point before that I want to think of this Kramers-Vonnier duality as a physical operation I can do to my system, because it will be important to actually realize this sandwiched operator where I have action on either side of the Kramers-Vonnier map. So if we now use all these equations that I had on the previous slide, I start with some truncated charge conjugation membrane on the Z3 toric code, and I push it back towards the paramagnet side. I'm going to leave behind at the boundary some trail. There's going to be some control operations that are spanning the paramagnet degrees of freedom and the toric code degrees of freedom. But the bulk of the symmetry membrane just passes through to the paramagnet, and then I can disregard it because it acts trivially there. And I'm just left with this boundary action, which it doesn't actually matter right now we don't need to worry about exactly what it looks like, just that it's some gates which have to act both on the paramagnet degrees of freedom and on the toric code degrees of freedom.
Sorry, Anna, just a clarification question. So you draw a lot of control gates on the boundary, if I'm getting correctly, so the control ones are part of the Z3 toric code is living on the edges of the square lattice, and the target ones are living on the sides of the square lattice. That
yes. That's correct.
Your drawing looks like they're on site.
Oh yeah, sorry. Yeah, the drawing is a bit imprecise, but yeah, correct. The paramagnet, the back square, the degrees of freedom are living on vertices of square lattice, and the degrees of freedom on the front square, the toric code side, are living on the edges. So now we have isolated some boundary action, which acts the same as this bulk truncated membrane of the symmetry. And because we have this boundary circuit, it now makes it easy to create an open line defect, because we can just cut this boundary circuit and only apply it on an open chain. But uh, as sort of pointed out, these control gates are acting on two different sets of degrees of freedom. So in order to be able to actually implement such gates in practice, we need to be able to access sort of both the paramagnet and the toric code degrees of freedom simultaneously. So we can do some control gates between them. And this is where sort of this physical operation of the Kramers-Wanier duality comes in, where we sort of the degrees of freedom, we can sort of partially apply Kramers-Wanier to the region of our lattice where the vertices live that need to act as our controls, so that we can sort of simultaneously in our system have paramagnetic degrees of freedom and toric code degrees of freedom to act this control circuit between. And then so this is where really where all the overhead in depth of our non-abelian ribbon circuits come from, is this unzipping procedure where we have to actually do this duality mapping between our topological order and the paramagnet. And then we do something finite depth, which is given by this boundary circuit, and then we redo the mapping back to sort of toric code degrees of freedom everywhere. So one point to mention is that because we're doing this Kramers-Wanier mapping in a finite region, there will be some boundary. And the stabilizers that live at the boundary of this region will not look symmetric to our Kramers-Wanier mapping. For instance, in A at the bottom, we can see that if I'm doing Kramers-Wanier along this purple line, then, and I'm going to sort of switch bases here, do a Hadamard. So I'm really gauging a prod Z symmetry rather than a prod X symmetry. A single X is not symmetric. And so when I gauge or ungauge this purple along this purple line, this vertex operator is going to get mapped to something non-local, because non-symmetric operators will become non-local in general under this Kramers-Wanier duality mapping. But this is sort of a feature and not a bug, because physically, this is how we can actually encode the internal state of our non-abelian excitation. This is how sort of boundary information in the sort of trivial paramagnetic phase gets mapped into sort of the non-local internal state of the non-abelian anion in the topological phase. And the way I can see this is because I'll have this non-local string that gets created, and then any anion that braids non-trivially with my anion pair I've just created has to cross this string. And so any sort of non-trivial commutation relations there will lead to sort of the non-abelian statistics that, Okay.
Yeah, maybe another question, sorry.
Yeah.
So before gauging, like in figure A, you draw a pair of X and Z stabilizers, and they like commute for trivial reasons. But it seems like after the entire procedure of like unzipping, zipping, etc., you're making them not anti, they're Q jumps.
Oh, yeah.
Sorry.
Yeah. Sorry, that's also so yeah, the figure here is a little misleading. I haven't drawn how this in figure A, that plaquette operator is mapped. They will commute afterwards. What I've drawn in the second figure is just
It's
generic
lots of
anion
braid. Yeah, I
that's
see, I see.
braiding with the anion pair that I've just created.
Yeah. You might need to clarify. Like I think there's a blue circle, like empty circle on top, right? That's your anion. You want to say that after gauging, it braids non-trivially with the bridge cut.
Yeah. No, sorry. Yeah, that was unclear.
Okay, cool.
Yeah, okay. So these are sort of hopefully illustrative examples in the relatively simple context of the Z3 and S3 topological orders to give a sense for how this procedure works. But in general, we can sort of do this mapping for generic finite group quantum double models. And sort of by defining some notion of group-based Paulis and writing down this generalized Kramers-Wanier map. And you can play a similar game where here on the right, I've depicted sort of a tensor network form of this Kramers-Wanier map, where the black degrees of freedom are my topological degrees of freedom, and the white circles indicate my paramagnet degrees of freedom. And by just, using the properties of this Kramers-Wanier map, I can push, for instance, this charge string through to the paramagnet side. And similarly to sort of the trivial abelian case, I will get sort of two isolated charge operators at the ends of the string on the paramagnet side. Similarly, as to this charge conjugation defect case, I can sort of play the game of cooking up some symmetry and symmetry operator. In this case, I'm restricting to symmetries that are at the level of the group, not at the level, not only at the level of the anion theory. So what I mean by that is that like charge conjugation, for instance, is automorphism of Z3 or as a group. But something like an EM duality symmetry is, only arises at the level of the modular data of my topological order. Is not reflected sort of in the group properties of Z2. So here I'm just focusing on things that I can sort of on group automorphism symmetries. And I can play the same game as with the charge conjugation, where I consider some finite membrane of the symmetry. I push it through onto the paramagnet side where it will generically act trivially, except for this boundary action by some control gates, which act generically between the toric code, between the topological degrees of freedom and the paramagnet degrees of freedom. Yeah, so just to summarize, have this sort of simple construction where we unzip, do something in general finite depth on top of the short range entangled state, and then rezip to leave behind the anion or defect of interest. And I want to, I guess, advocate for this as both maybe a nice constructive way of writing down circuits for use in like near-term devices, but also a conceptual framework for understanding kind of where the structure of these non-abelian anions and defects comes from. And just to sort of drive this point home, I can go back to this original ribbon formula that I flashed at the beginning. And actually, if you, for instance, for S3, you can write down explicitly, at the level of qubits and qubits, how a circuit, for instance, for an S3 anion looks. And doing some playing around with gates and things like this, you can decompose this circuit into exactly these ungaging and regaging steps that I've been talking about. So really, in the original ribbon formulas, the structure is already there. So kind of able to sort of make a connection with the known formulas for these non-abelian ribbons. And then another remark is that I mentioned that there was previous work exploring how to efficiently create non-abelian anyons by using adaptive circuits. And we are able to also do the same, and we can pinpoint the reason for the existence of these adaptive circuits is because sometimes if your symmetry group has the right properties, you can make this gauging map finite depth rather than linear depth. And in particular, work done by Nat and Rubin shown that gauging symmetries corresponding to solvable non-abelian groups can be made finite depth with measurements and feedback. And so solvable anion theories thus can have sort of efficient defect and anion ribbons. And S3 is sort of a nice example to work with because it is solvable. So it does have these efficient ribbon representations, but it's also universal for quantum computing through both using braiding and fusion of its anyons. So it presents sort of a nice opportunity in the near term for realizing universal topological quantum computation and doing it efficiently. Another sort of application remark is that we can use the same ideas to construct ribbons for twisted quantum doubles. So now instead of starting with some trivial paramagnet, we start with an SBT and then apply Kramers-Vonnier, and we'll generically obtain some twisted topological order. And everything sort of remains pretty much the same, but now we have to take into account how our symmetries can fractionalize on the dual SBT, which will, in general, add some extra structure to our ribbon operators. And in our paper, we worked out ribbons for doubled semyon, for D4 and quaternion topological orders, which have expressions as sort of conventional quantum doubles, but are also equivalent to some twisted quantum doubles with so-called type 3 cocycles. So just to flash sort of what these ribbon operators kind of look like, the last two rows here give just, you don't need to know what this means, but just to show you that we have some explicit expressions if you're interested in looking at them in more detail. And then a last remark, I've sort of been emphasizing that part of our motivation here was really looking for ribbon expressions that would be sort of tailored and easy to use on quantum devices. And indeed, recently we've had nice collaboration with some people at Quantinuum, where we used these circuits that I've discussed for the charge conjugation defect to actually create and manipulate these defects inside the Z3 toric code. And yeah, so that is also out if you're interested. Yeah, so then just to finish up, I've gone through this generic recipe, and I think the conceptual framework is simple enough that I can envision that it might be useful for things outside of this quantum double regime that I've focused on today. Maybe, find some way that this applies to understanding structure of string nets, maybe beyond 2D codes, or perhaps, I talked about some restricted class of symmetry defects today. I, for instance, didn't cover sort of EM duality defects. So we're thinking about some ways of expanding this framework to that. Can we use sort of this same recipe and interchange some other duality mappings of interest to get something useful? And then finally, from the more sort of quantum computing side of things, all of this is at least sort of all of the realizations that we've worked on with the people on Quantinuum, right? And most sort of digital quantum devices, the realizations of these topological orders are done sort of at a state preparation level and without sort of some actual Hamiltonian dynamics, which are cooling your system and doing passive error correction for you. So any sort of actual practical use will rely on the fact that we have some way of doing active error correction and have some way of making all of these things fault tolerant. So as of now, we don't have a way to do that, but I think certainly a question that needs to be answered. Yeah, and with that, I'll just say thank you for listening. Yeah, and any questions?
Any questions? So I have one regarding the experimental realization. I know it was just like a very brief thing that you showed, but kind of just as a sentence, a couple of words, how will we know that this actually is realized in an experiment? What will be the signature?
So yes, we actually measure the stabilizers of the Z3 Tora code. So we have we're able to estimate some fidelity of how close we are to the actual Tora code ground state.
And how large is the system?
Yeah, the largest system size we were able to prepare is 4x4 lattice, but on this rotated Wen plaquette type model, so our degrees of freedom are actually at the vertices of the square lattice rather than edges.
Any other questions?
I do have one. So maybe you talked about this, but I missed it. So as far as understanding, gauging is easy to control if or not there's a gauge flux, right? So if you unzip and you put a defect there, you know that there's some flux after you zip it back. But the charge sometimes is more difficult to control. So I guess it refers to basically whether or not you have exact control over the quote internal state of the anyon, which they're not topological data, but maybe you do care about them for some purpose. So do you have control over the internal state as well? Any internal state?
Yeah. So maybe if I go back to this picture. So the there will be sort of I don't have it pictured here, but this plaquette in part A will also be mapped to something non-local. And so sort of the value of the by toggling sort of the value of the stabilizer sort of during the intermediate state where before you fully gauge back to get the non-local thing, you can have control over the eigenvalue of this non-local stabilizer. And that will correspond, having different eigenvalues of this non-local stabilizer will correspond to different internal states of the resulting non-abelian anion pair. But yeah, so in that sense, you do have control over which internal state you actually get at the end.
In other words, you can fully recover all the string operators with all these dangling disks.
Yes. Mm-hmm. Yeah.
Any other questions? All right, if not, let's thank Anna once again.